Okay. Hi, everyone. So today, last session, at the end of last session, we talked about Siemens networks, and we were gonna review that again very quickly and continue with that. So metric learning by Siemens networks, we said that one of the techniques for deep metric learning is Siemens network, which is used for feature extraction, yes? And we said that it has several sub networks which share their weights, right? And then I said it was proposed in 1993, and I said if there are three networks sharing their weights, we also call it triplet network. And so usually we have two networks or three networks. The two networks for Siemens networks with two networks usually has contrastive loss, and Siemens network with three networks usually has triplet loss, right? And I said that it is a supervised. It is kind of semi-supervised. I will tell you why. Semi-supervised learning, and so its idea is the same as the idea of supervised dimensionality reduction. What was the main idea behind supervised dimensionality reduction? What was that? It was saying that its idea was decreasing the intra-class variances and increasing the inter-class variances to separate the classes as much as possible, right? So that was what we talked about. And so yeah, here we said that. So Siemens network does that. And it has been used in different applications such as computer vision and natural language processing, NLP. So we said that we make pairs or triplets of data points. How? We say for example, let's consider triplets. What do I mean? So we have a data set, and then we extract triplets of anchor, positive, and negative from the data, where anchor and positive belong to the same class and negative belongs to the different class, right? In this case, we'll have triplets, but we can also have pairs of anchor positive and anchor negative, right? So both are possible to generate out of data. A good thing is that we can also generate positive points by augmenting the anchor point, because positive and anchor should belong to the same pattern or same class, right? When we have the anchor point augmented, what do I mean? Rotate it a bit, add some noise to it, right? Do some data augmentation techniques on anchor point to get the positive points. So that's another thing. Also, why do I say semi-supervised? What is semi-supervised learning in machine learning? It is when, you know?
Okay, so you can manually label some data.
Okay.
Just part of the entire training data. And let the model to label the data based on this main label.
Yes.
Data to
yes.
learn.
Yes. Thank you. So I can say that whenever your algorithm can generate labels by itself, that's called semi-supervised learning. So because in supervised learning, you're assuming you have the labels. In not unsupervised learning, you don't have labels. In semi-supervised learning, you don't have labels, but your algorithm can generate labels out of data. So this is what it is called. And thank you very much for answering. So I'm saying that Siemens network can be used for semi-supervised learning. Why? We can generate triplets out of data even when we don't have classes in some cases. What do I mean? Consider the data, image data, big images, okay? At least there are two applications in my mind that have these kinds of images, two big images. One is aerial images by satellites, right? Or by airplanes, whatever, to get the map of the cities, right? Another one is histopathology images, where you have huge, so because they get some part of the body out, they put it under the microscope and they zoom it. So it has a huge zoom and it has megapixels. Okay, so a huge image. So at least these two applications Then what happens? There is a technique named Tal-Tuvek. There is a paper on that. What does it do? It says either in the map by aerial images or in histopathology images, there is a hypothesis that the closer patches have more similar patterns. Agreed? Right? But the distant patches will probably be different. What do I mean? For example, here, if it is a house here, apparently, seemingly, here also have a house next to it. Or there might be two patches on the roof of the same house, right? But here, there might be a garden or a street. So they are different, right? With high probability. So in this case, we can generate triplets where anchor and positive are patches close to each other with some radius, and negative is a patch away from it. Again, it works for both histopathology and aerial images for maps. And it's called Tal-Tuvek. So as I said, we can generate triplets out of data even without labels. We can also augment the anchor to get the positive points. Okay. Also, we can generate the triplets using the patterns of anchor, positive, and negative. So I'm using the patterns of the data points. If 2 points have similar patterns, I can assume they are anchor and positive. If they are have different patterns, then I can assume it to be anchor and negative, right? So we denote anchor positive and negative by superscript A, P, and N, right? And we said that we have several loss functions for them. I think we stopped here, right? Yes. No. So I said for subnetwork, we can have different backbone networks. What do I mean by backbone network? The network that we can use for inside the Siemens networks. It can be fully connected network. It can be convolutional neural network. It can be ResNet, anything, right? LeNet. So you can use anything. For example, if your data, anchor, positive, and negative, are images, then you can use convolutional neural network, right? Agreed? Do you agree? Yeah. Okay. So, and I said, how do we implement them? Rather than having several networks in the memory, we usually have one network and feed it several times. Feed anchor to it, feed positive to it, and feed negative to it. So it's more memory efficient. I think we stopped here. Loss functions for Siemens networks. Okay. So one loss function for Siemens network is contrastive loss. Let me remember. Yes. Contrastive loss was proposed by Facebook. Nowadays called Meta, right? I think, as far as I remember. LeCun et al. Proposed that. LeCun is the head of AI in Facebook, right? So it uses anchor positive and anchor negative pairs. So contrastive loss uses pairs, but triplet loss uses triplets. Okay. And what do I mean? Suppose in each mini batch that you have, we have B pairs of points. Okay. So basically, I'm assuming that my mini batch size is 2B, where I have B pairs of points, xi1 and xi2. Okay. Some of which are anchor positive and some of them are anchor negative pairs. Are clear? Okay. Then the points in the anchor positive pair are similar, of course, right? The pairs in the anchor negative pair are dissimilar. So I denote similar by S and dissimilar by D. These are sets, right? Then what do I say? Now we define yi, which is a scalar. If the pair is a anchor positive pair, then yi is 0. If they are anchor negative or they are dissimilar, then yi is 1. So I goes from 1 to B here, or NT. You can see it as a number of triplets or pairs, doesn't matter. So what is contrastive loss? By the way, we have different variants of contrastive loss. For more information, you can see our tutorial paper. But the main contrastive loss, which was proposed in 2006 by Facebook, was this, equation 11. Let's analyze it. So what is it? So I have summation over batch as always, right? And then so minimize with respect to theta. Theta are the weights or parameters of the neural network. What is this? We already talked about it in the previous session. This is the distance of embeddings of xi1 and xi2. What do I mean? So feed xi1 to the network, it gives you fxi1 as output in the embedding. Feed xi2 to the network, it gives you fxi2, right? And in the embedding or output layer of the neural network, right, you take the distance between them. It can be Euclidean distance or squared Euclidean distance or any kind of distance that you use, right? And then, so 1 minus yi, when is it 1? When yi is 0, right? So when they are similar. And also here, I have yi. Basically, it means that whenever I have anchor and positive, I will have the first term. Whenever I have anchor and negative, I will have the second term. So far clear? Hi. Okay? Did you get it? So now, okay, so consider the first term. When I have anchor and positive, it means that minimize their distance. Of course, we want them to be close to each other in the embedded space, right? Minimize the distance between. When they are dissimilar, the second term turns on, and the first term turns off, right? Then now I will have this. So what is this? You tell me. Basically, do you remember this is a standard hinge loss, which is similar to the ReLU function, right? It's called a standard hinge loss. And this M is a positive scalar. It is a margin. So basically, it means that, by the way, I have minimized minus this distance. What do I mean? It is equivalent to maximizing that, right? So, of course, we want to maximize the distance between anchor and negative in the embedding space. So it makes sense. But plus M in the standard hinge loss, it means that increase their distances in the embedding space, but up to the margin M. As long as the distance becomes margin M, stop. Okay, did you get it? So basically, the whole thing, the whole loss is saying that push positive and anchor toward each other. Hopefully, at the end, maybe they collapse onto one point, or they become very close to each other. But for the dissimilar points, push them away from each other until the distance between them becomes M. So far clear? Okay. So it makes sense. Interesting. And this is what we had. This is exactly, I have denoted that here. So push positive toward anchor and push the negative away from it. So this is one pair, this is another pair, right? And yes, we already talked about this. Minimize the embedding distances of similar points and maximize the embedding distance of dissimilar points. The same idea that as Fisher discriminant analysis that we had in a century ago. So basically, this figure B is a contrastive loss. As you see, anchor and positive become very close to each other, or maybe they fall on each other. But anchor and negative, they will have the distance M. And the moment that this distance becomes M or larger than M, then this becomes 0. Right? Now let's talk about triplet loss. Triplet loss was proposed, as far as I remember, by Google. It was proposed in 2015. There was a paper where they named it FaceNet because it was for face recognition. But in the same paper, they proposed triplet loss. So what is it? So of course, triplet loss uses triplets data points, right? And this is the loss. What is it? So again, it has a standard hinge loss and also the margin M. But as you see, the whole thing, by the way, I don't have yi anymore here because yi was for pairs. But here, the whole thing is inside the standard hinge loss. So what is this? This is the distance of embeddings of anchor and positive. What is this? The distance of embeddings of anchor and negative. I'm minimizing this, obviously, as expected. I want to minimize the distance of anchor and positive in the embedding space. I'm minimizing minus this. In other words, I'm maximizing this. Of course, as expected, I want to increase the distance between anchor and negative, right? But now let's analyze the standard hingeless here. What is it saying? When does this become 0? When does this become 0? So the whole thing, loss, when the loss becomes 0, training stops, right? Because minimize 0 function with respect to theta. However, you change theta, 0 doesn't minimize. 0 is 0, right? So when does this become 0 or negative? So whenever it becomes 0, it stops. When does this become 0? When inside the standard hingeless becomes negative, right? Agree? Do you agree? So now let me write it down. F of. So I denote f of xi a by fa to be faster. Fa and fp minus d of fa minus fn plus m to become negative. Right? When this happens, training stops. Now rearrange the terms here. You will get this. So I bring this to the other side, right? So the desire of the triplet loss is this, equation 13. Now let's visualize this desire. What does it mean? That let the distance of embeddings of anchor and positive plus m be less than or equal to distance of anchor, embeddings of anchor and negative. In other words, I want to push away the negative from anchor. Also, at the same time, I'm pushing the positive toward anchor. So basically, I'm doing this. I'm also pushing this toward this, right? Until the distance, this distance, what is this distance? Distance of positive and negative becomes m, right? This is exactly, what is m here? That this difference between distance of anchor negative and this distance of anchor positive, right? So this is triplet loss. Do you see now? Compare figure B and C. Do you see the difference between them? Do you see that? Both of them are increasing the interclass variances and decreasing the intra-class variances, right? Both of them, but with a bit different functionality, with different functions. Did you get it? So this is triplet loss. But they both have the same idea as Fisher discriminant analysis. Also, there's another loss named neighborhood component analysis, NCA. It was proposed in 2005, not for deep learning. Because, you know, in machine learning, initially, before the era of deep learning, they always had simple gradient descent, for example, for optimization, right? Later, when deep learning came, they said, okay, let's implement it in by backpropagation in deep neural network, right? So initially, it was proposed in 2005 by Hinton et al. For a spectral metric learning method. They used simple gradient descent, but nowadays they use it in neural network, in Siemens neural network. After the success of deep learning, it was used as a loss function of Siemens network, where we minimize the negative log likelihood using Gaussian distribution. Do you agree that we can maximize the log likelihood, maximum likelihood estimation? Agreed? But in neural networks, we don't have maximization. We usually minimize in the libraries, right? We use gradient descent. We don't use gradient ascent in backpropagation. As a result, we minimize minus log likelihood. Minimize the negative log likelihood using Gaussian distribution. How do we make the Gaussian distribution? Softmax form, right? So we have the distances. We have a bunch of data points. We bunch of values. We want to make it like probability, but Gaussian probability. What should we do? We can use softmax, right? Softmax form. In this case, they will be between 0 and 1. They will sum to 1, and they will also behave like Gaussian distribution because of exponential operator. So in the numerator, by the way, I have summation over the batch, minus because it is negative log likelihood, right? And log because of log likelihood. Here, in the numerator, I have e to the power minus d of embeddings of this minus distance of embeddings of anchor and positive, right? Now let's, and in the denominator, I have the distances of pairs of anchor and negative in the embedding space. Now let's analyze it. Does it make sense? Minimize minus something. In other words, I'm maximizing this thing, the whole fraction. So logarithm is a monotonic function. So maximizing the logarithm is equivalent to maximizing its argument. So maximize inside the logarithm. Maximize the fraction means maximize the numerator, right? So we are sorry, give me a second. Minimize minus something, maximize this thing. Yes, I was right. So maximize this numerator. What is numerator? E to the power minus d, right? So maximize e to the power something is equivalent to maximize that power. So maximize minus d, right? Here I'm talking about. Maximize minus d is equivalent to minimize d, right? In other words, I'm minimizing the distance between anchor and positive as expected in the embeddings. Now, come back again. Minimize minus logarithm equivalent to maximize logarithm equivalent to maximize inside the logarithm. So maximize the fraction equivalent to minimize the denominator. Minimize the denominator. So minimize e to the power minus d. In other words, minimize minus d. In other words, maximize d. So we are maximizing the distance of anchor and negative as expected. So it makes sense. This last function makes sense, right? And as you see, we are using triplets, so it can be used with Simon's network. Triplet mining. By the way, feel free to interrupt me whenever you have any question, right? In every mini batch containing the data points from C classes, we can select and use triplets of the data points in different ways. So when we want to generate the triplets, one way to do that is to generate them randomly. What do I mean? So get anchor randomly or from some the batch, and then for that anchor to generate the positive, you can randomly select one of the points from the same class, right? Also get negative randomly from another class, right? This gives you the triplet. However, who says that we should always do it randomly? We can also choose the triplets wisely, right? And this is called triplet mining. For example, all similar and dissimilar points, we can take all of them, all of the similar and dissimilar points. So all possible triplets, that's also one possibility. Another approach is that we use some of the similar and dissimilar points, and that's called triplet mining, as I said. So there are several techniques. First off, suppose B is the mini batch size, CXI is the class index of XI, and XJ denotes the points of the jth class in the mini batch, okay? XJ. And X denotes the data points in the mini batch, okay. But one of the methods for triplet mining is called batch all. Okay, it was proposed in 2015, not very old. So it considers every point in the mini batch as an anchor point. What do you mean? So you have the mini batch, consider, because you want to generate triplets, right? Consider for every triplet you consider one of the points as the anchor. In other words, if your batch size is B, you will have B triplets, right? Where every point in the mini batch is anchor in one of the triplets. Then all points in the mini batch which are in the same class as the anchor are positive points, become positive, and all points in the mini batch which are from the different class become negative points. And you can see we will have a lot of triplets, right? And so as you see, I have summation over the backs, and this first summation you can see it as a summation over the anchors, right? Then summation over the positives, all of xj's which belong to the same class as xi, right? And then the third summation is the summation over the negatives. So you can see it as a nested, three nested loops, right? And then you will have the triplet class that we had. So it is using all available information. Of course, it's computationally expensive, right? Batch hard. Each of these is a paper, right? Batch hard triplet mining, it was proposed in 2017. So what does it do? So it considers, you tell me without looking. Assume I have candidate positives, anchors, and negatives, right? So for an anchor, what is the hardest triplet that we can make for to be hardest for the neural network, for the Siemens network training? We want to take very hard on the neural network training. What is the hardest case? Can you answer?
If it was further than the similar case.
Yeah, okay. So what? Yeah, can you explain more? So you are right. Let me rephrase it. So I have anchor. I have a bunch of points from the same class, right? So a bunch of candidate positive points. But which one is the hardest? The one which is farthest away, the most different pattern from the anchor, right? Most different pattern from the anchor, I take it as a similar point because the network should push that toward the anchor. And it becomes, but it is very far away. So it's hardest case, right? What about negative? The hardest case is that the negative is closest to the anchor, right? And so batch hard is that. Batch hard says consider the hardest positive, which is the farthest point from the anchor point in the same class. By the way, when I say farthest point in the input space is equivalent to farthest point in the embedding space. Agree? Because usually when its pattern is far away in the input space, in the embedding space, it will also fall far away from it. So the hardest negative also, which is the closest point to the anchor point from the anchor from another class, right? So in other words, batch hard is that. So we use a triplet loss, but as you see, so summation over the batch or over the anchors. But for positive, I choose the hardest positive, maximum distance, right? And for the negative, I choose the hardest negative, minimum distance, right? So why does it make sense to do that? Because they say let's take it hard on the network. If it can learn the hardest cases, it is expected to cover also other cases, right? When you take hard on your neural network, it will learn the easy cases as well. This is the intuition behind that. This is also related to the opposition-based learning. Opposition-based learning basically says whatever you learn its opposite as well. It was proposed by Hamid Tishoush, who was a professor in U Waterloo, but he left and he's in US now. Opposition-based learning. Okay, so batch semi-hard. Batch semi-hard, what is that? It says that it was proposed in 2015. It says consider every point in the mini batch as an anchor point again, but all points in the mini batch which are in the same class, let them be positive. So far it is similar to batch all, but for negative, take the hardest negative, which is farther than the positive point. The hardest negative, which is closest to the anchor, but there is a but, which is farther than the positive point. Okay, so for every triplet, we have the anchor and positive, right? So positive is known for every triplet. Then for negative, for selecting the negative, get the hardest negative, which is farther than that positive from the anchor. Okay, where this condition means that it is farther from the negative, from the positive, and we are using the triplet loss. Do you see that? Okay. Another one is easy positive, proposed in 2020. Close to the state of the art, right? So now it's very close to us. And it considers every point as the anchor. The easiest positive, closest to the anchor point from the same class, is used as the positive point. So they take the easiest case, and all points from the different class as the negative. So for the positive points, they consider the easiest case. That's why. So here, summation over the anchors, summation over the negatives. What is this notation? This means subtract for sets. Okay, subtract for sets. So x minus all of the x's which are in the same class as xi. So it's summation over the negatives, and this is the easiest positive. We can also use triplet mining in NCA, neighborhood component analysis loss function, right? So it shouldn't just be used for triplet loss. It can be used for NCA loss as well. Here you can see, for example, we are using that one of them. So here, let me think. So minimum of this basically means the closest similar point, right? So here also we are using closest similar point, and these are the negative poles. So this is easy positive for NCA. We can also have other triplet mining methods with NCA as well. I know these parts are easy. We are going fast on them. I know these parts are easy. Okay, so we can also have triplet sampling. Rather than using extreme positive or negative points, the hardest and easiest. These are the extreme cases, right? We can sample positive and negative points from the points in the mini batch or from some distribution. So first off, let me tell you, we have two types of sampling in the literature of statistics. One of them is, for more information, read this paper. Give me a second. So I have a tutorial paper named Sampling Algorithms from Survey Sampling to Monte Carlo Methods, Tutorial and Literature Review. So what is it saying? So two methods for sampling. Either these are two sampling methods in Department of Statistics. So survey sampling means that you sample, you have a set of something, set of some values, and you sample from those values in the set. Okay. Example. For example, census. You know census? You count how many people are in each town in the country, right? Something like that. Or simple random sampling with replacement, without replacement, a stratified sampling, right? These things. Another method to do sampling is when you have a distribution and you sample from this distribution, like a Gaussian distribution, whatever, some distribution, and you sample. So as you see, you're using sampling in two different senses. So the first one, sampling from a set, is called survey sampling. Sampling from a distribution is called Monte Carlo method, Monte Carlo sampling. Why did I say that? Because here we say we have triplet, we have some data points, we want to sample from them. If we sample from the data points in the batch, it's called survey sampling, right? Called service. But what if I consider the distribution of the classes and I sample from the distributions? In this case, I do not necessarily sample from the points in the class, in the data set, right? So it might be some interpolated point between 2 points in the data set, right? When I sample. In this case, it's called Monte Carlo sampling. Okay, that's one thing. So here we can say there are several approaches for the positive and negative points to be sampled. Sampled by extreme distances of points. Okay. Sampled by randomly from classes, of course. We already have talked about these things, I think. Sampled by distribution, but from existing points. So it comes kind of survey sampling, and sampling stochastically from distributions of classes, which is Monte Carlo sampling. Right? By the way, why is it called Monte Carlo? Yeah, so they had a secret project, Van Neumann et al. They had a secret project which was related to probability So they named it Monte Carlo because it was in the Monte Carlo city, apparently. And from that time, Monte Carlo remained in the area of probability. Okay, so that's the reason. A bit of history. Okay, so where were we? Okay, the first, second, and third, these ones, sample the positive and negative points from the set of points, as I said. But the third one from samples from distributions stochastically. Stochastic means probabilistic, right? Deterministic means non-random. Stochastic means random. An example for the third approach is sampling by distribution from existing points, which is distance weighted sampling proposed in 2017. Another one is Bayesian update sampling by Bayesian updating theorem proposed in 2021. This is our paper. Sampling by Bayesian updating theorem is our paper. I remember it when I worked on this paper with Milad, one of my friends. So what is Bayesian updating theorem? Do you know that? Consider some distribution and consider your data to be a streaming online data. It is coming, okay? Then your distribution might change. So initially, it might be some distribution, but when the new data comes, the distribution changes. So you will have a dynamic distribution changing over time. And you can update that distribution by Bayesian updating theorem. And why do we use that in triplet sampling? We want to sample from the embeddings of classes in the embedding space. Okay, you get my point? So whenever a batch comes in backpropagation, right? A batch comes from data, then I can see where they fall in the embedding space, output space of the neural network. Agree? And the batches are coming, so it's a streaming data, right? Also, the neural network weights are changing because of change of weights of neural network during backpropagation, and also newly coming batches. Because of both of these, the distribution of classes changing the embedding space, right? So we need to update the distributions of the classes by Bayesian updating theory, right? And then we sample from the updated distribution in every mini batch. Interesting, right? So you can do that. Okay. Acknowledgement. This slide deck was based on our tutorial paper, Spectral, Probabilistic, and Deep Metric Learning Tutorial and Survey. That also you can see the chapter Deep Metric Learning in our book, Elements of Dimensionality Reduction and Manifold Learning. And for more information, as I said, we in the tutorial paper, we have covered a lot more, but this was just an overview of important things. Any question? No? So these are the references. FaceNet, you see, but the paper of Google for triplet loss. Yes. Okay, these were the references. Now let's move on to the next topic if you don't have any questions. Wait, you are very quiet. Does it mean that this is boring? No. Let it be interactive, please. Ask questions, challenge me or something. Okay. The next topic is deep reinforcement learning. So first off, let me confess that I'm not an expert in this area. Okay, so I don't know everything in this area. But my duty is to transfer whatever I know, my knowledge to you. Okay, so this is my limited knowledge, but I want to transfer it to you. Okay, I hope that I can teach it well. This is the first semester that I'm teaching RL. And I think it's good. I know there is a whole course on RL, but here I give a condensed version of RL as far as I know. Okay, and I think it's worthy, in my opinion. So I don't know everything, as I said. And if you might know better than me. If I make any mistake, let me know. Okay, correct me. So deep reinforcement learning. So reinforcement learning, or RL, in short, it is an area in machine learning where where we have one or several agents or players, whatever we call it, which take actions in an environment to maximize their cumulative reward. I will tell you what these mean. So first up, RL is the same as how you train a dog or animals. So what do I mean? I have explained it in this paragraph as well. So assume I have a dog and I want to train it to come to me whenever I come home. Okay. So I buy the dog, I put it in the house, then I go out, I come back. I open the door, the dog doesn't move. Okay. So I don't feed the dog. I give it hunger. Okay. For hours. Then the dog might say, what a cruel owner I have, but it might not find out the correlation between not coming to me and hunger. It might not find out initially. Next time this happens again, this repeats, and I don't feed the dog. But the dog, it depends on how smart the dog is. At some point, maybe after several days, when I come home, suddenly, randomly, the dog comes to me. Randomly. Okay. So it randomly makes an action which doesn't know whether it's good or not. But it comes to me randomly. I feed the dog. Okay. Then this happens several times. After several trials, the dog finds out that apparently there is a correlation between coming to me and being fed. Right? In this case, the dog will repeat that thing which is rewarding, that action. Right? So in this case, whenever I come home, after some time, the dog will come to me. Agree? So this is how they train animals. Also, this is how they train animals in zoos. In zoo, have you seen that the person takes some stick and the lion stands on its legs, right? How does it do that? So exactly with the same way. The lion doesn't stand up. They punish the lion, but whenever the lion stands up, they will reward it. And after some time, the lion finds out that whenever the owner takes the stick up, it needs to stand up to be rewarded, right? So this is how they train animals. Now, someone said, why not considering AI or machine as an animal? Let AI be our animal to train it. Okay. In other words, the AI will make actions initially random actions, right? And then the machine, after some time, will find out the correlation between the actions, the good actions and good rewards, and bad actions and bad rewards, or not having rewards, right? And how does it find out the correlation? Can you tell me, how do we do it in mathematics? Can you give me guess what? What? Wait. So yeah, so assume we have some rewards, maybe you can see it as weights. So I'm saying that assume we have actions, we have rewards, we have environment. And how do we model this? Let me tell you that we model it by optimization. So we have some cost, we minimize it. I have said it several times in this course that all machine learning is optimization, plus some other things such as probability and linear algebra. Machine learning always breaks down into optimization. So you are always minimizing some cost function or maximizing some fitness function. Okay. So we'll see that they model it by optimization. And here, agent or player is the animal, right? And in what is environment? Where the agent is playing. We'll see some examples. So the agent makes some action in the environment, and the environment will react, and so it will have some state. What is a state or observation? The situation, realization that the environment will have at every time step, right? And it will change by the actions of the agent, right? If I move this table, the table will fall. When the table is fallen, that's a state of this classroom, right? So also, we might have multiple agents cooperating with each other. What do I mean? Assume Consider the environment in this class. Okay. Then what happens? We have some, assume rather than one player, I have several players, several agents. What do I mean? Assume the environment is big or complex. Rather than having one agent to learn the environment, what do I mean by learning environment? When the agent goes and does some actions in the environment and they see the state, the reward, they will learn this environment. Apparently in this part of the environment, if I do this, it's good. If I do this, it's bad, right? And this might differ depending on where it is in the environment, right? Whether it's, for example, in this environment, whether it's there or there. The action might differ. Which action is best in the bottom left corner, bottom right corner? What is the best to do in bottom left corner, right? So rather than having one agent to explore the whole environment, let's have several agents, right? And they cooperate with each other. What do I mean? When an agent learns there, the other agent doesn't need to learn that corner anymore, because that agent learned that and will let the other agent know what it learned. Okay. By the way, so this is called multi-agent reinforcement learning, or MARL. Okay, these are advanced reinforcement learning algorithms. By the way, again, there are several ways. So as you see, it's a distributed algorithm. Why? Every agent is learning by its own, and they will collaborate with each other, the information, right? So you can see them as servers, different servers. So it's a distributed algorithm. We have at least two broad ways to do distributed algorithms. At least there are several. There are two broad ways. Can you tell me what? So I have a bunch of servers, they want to collaborate and cooperate with each other. Can you tell me how you can implement them in coding language, whatever? What? Synchronize. Yeah. Yes, again, that's also a part of distributed algorithms, whether they are synchronized or asynchronized, but I'm not talking about that. Okay, let me tell you. Either I have a central center that the other servers will send to that central server. The other servers will send the information to the central server. The central server will process it and they will share the information back to them, right? Assume I have a central server, central agent. That agent learns something there, will send the information to this central agent. Also, that server learns something there and send the information to this central server. And the central server will share the information to both of them. So it will say that agent 1 learned this, send it to agent 2. Agent 2 learned this, send it to agent 1. Okay, that's one way. But this way has a big flaw. What is the flaw of this way to do distributed algorithms? Consider yourself to be a hacker and you want to shut down the whole system. What do? What? You attack or shut down the central server. Whenever the central server goes down, the whole system goes down, right? So it's very bad for security, right? So how can we be robust to hackers' attacks? Simply, we shouldn't have any central server. What do I mean? Let the servers collaborate with each other, cooperate with each other directly. Of course, if we might have a lot of servers, maybe server 1 and server 100 are very far away from each other to collaborate. That's fine. Server 1 can send to server 50. Server 50 can send the same information to server 100. So they might do it by some middle servers, right? They might two servers might collaborate with each other with the help of other servers, right? This is called peer-to-peer networks. Okay, and we see it in telecommunications. There is also one illegal platform for sharing movies, etc. That also uses I don't say the name because it's been recorded. That's also using peer-to-peer networks. Why do they do that? Because they don't want government to shut down the system. If the government shuts down one server, there are 100 other servers which are working. There is no central server. Otherwise, the government could easily shut down that server, central server, right? So that's one thing. And this is also related to distributed algorithms. And another part that we have distributed algorithms in machine learning is called federated learning. What again, federated learning is the same thing. We have a central server, we have a bunch of servers, and these servers have a copy of neural network, some neural network, okay? And they have their own data, okay? They own it. So the servers don't have access to each other's data. They will train one epoch or whatever we call it, one step or epoch of training on their own data, and then they send their weights to the central server. The central server, by the way, the architectures of these servers are usually the same. The central server will take the average of the weights and then will send the average back to them. They will copy the average to their weights again and do one other epoch of training using their own data, right? So this is called federated learning. It has different variants, but one good thing about the federated learning is that it can be used for privacy. Why? Because the servers don't see each other's data, right? So for privacy and security, that's also useful. Okay. Consider the game of tic-tac-toe. Okay. And let's see for different elements of the reinforcement learning. One of them is environment. Environment is the environment in which the agents play. For example, in tic-tac-toe, this is the environment. You see that? Action. The action which agents play. For example, the one action is this, putting a cross here, right? And state. What is a state? The state or realization or situation of the environment. For example, this is one of the states of the tic-tac-toe game, right? But reward is when the agent wins or does something good, Better actions have more rewards. For example, in this game, this is the reward because it has won, okay? Not necessarily winning has only reward. Doing something good also has some reward, okay? And by the way, let's talk about the state a bit more. State S, okay? What is this? Let's see some examples. It can be any vector or matrix representing the state of the environment. Example, in tic-tac-toe, what is the state? It is a 9-dimensional vector. Why? Because we have 9 cells, right? And each element of the vector can have 3 possible values, right? One for empty, one for cross, one for certain, right? So how many permutations of states do I have? How many states do I have? What is my state space dimensionality? State is 9-dimensional, but I mean, what is the number of states in the state space? It's 3 to the power of 9, right? It's large. Also, in inverted pendulum, the state is a 4-dimensional. What is inverted pendulum? Do you know that? No? So consider this a cart where there is a pendulum which might fall from any side, right? It's unstable. See my hand? And I need to move the cart to the right or left. If it is 2D, it might be to the front and back as well. Doesn't matter. So I move that so that the pendulum doesn't fall. The inverted pendulum doesn't fall. Can you see? Can you give me some real-world examples of inverted pendulum? So unicycle. Have you seen the unicycles? In Canada, some people use that. It's like a bicycle, but it has only one wheel. They stand on it and they move. If they don't control it it's an inverted pendulum, right? The person will fall. That's one thing. Another more serious application is launching the shuttles and rockets. When NASA wants to launch a rocket, right? So in military applications, also in aerospace applications, SpaceX, NASA, whatever, they also use the inverted pendulum. Do you know why? Because initially, when they count down from 10 to 1 before launching, the bases are at the bottom of the rocket. So it is not an inverted pendulum. It's stable. But when they count to 0, they release the bases, and after several seconds, they fire the engine. After firing the engine, it's not inverted pendulum. Before releasing the bases, it's not an inverted pendulum. In those few seconds, if they don't control it, the rocket will fall even before firing the engine because it's very heavy. Right? So they have to control it, and it's a very important problem in control theory. For example, until several years ago, at least, I know that NASA was using fuzzy controller or inverted pendulum. Do you know why? You know fuzzy logic? Do you know fuzzy logic? I already talked about it in the preliminaries. Fuzzy logic was developed by Lotfi Azadeh, right? Lotfi Ali Asgarzadeh. And he was a professor in the University of Berkeley. And you know that University of Berkeley is funded by the military department of US. So he had a project. So fuzzy was developed by the US fund of military department. Okay, anyway. So another example. So by the way, for inverted pendulum, the state is 4-dimensional vector having values for position, velocity, angle, and angular velocity. Okay. What about Atari games? In Atari game, the state is a frame, which is RGB image of the game at the current time. At every time, the frame changes, right? So state is dependent on the time. In the game of Go, what is game of Go? You know chess, right? Similar to chess, we have another famous game in East Asia. So it's called Game of Go. They have a bunch of stones, white stones and black stones. And there is a board with a lot of dots on it. They put the stones, they usually put it like this. They put the stones on the board. And it has some instructions I will let you know in a few slides. So Game of Go or chess or these board games, what is the state? It is a matrix or reshaped vector having values of the cells of the board game. For example, in Game of Go, I don't remember how, assume 10 by 10 dots. So we'll have 10,000, right?
It's our Go game, right?
Wait. Yeah, so I'm saying an example. Assume I have 10 by, it was more, but assume it was 10 by 10 dots. So we'll have 100 cells. Then each cell will have 3 possible things. Either it's empty, black stone, or white stone. What about chess? It's 8 by 8, 64. How many possible cases every cell has? A lot. Either it's empty, or pawn, or queen, or king, or rook, etc. Right? So I think now you understood what the state is. Now we should start with Markov decision process. Before that, I need to explain Markov process. So before Markov decision process, I need to explain Markov process. Have you passed any course on Markov model, hidden Markov model, discrete time Markov model, continuous time Markov model? Have you passed any course on that? No? Don't worry, I'm gonna explain this to you. So consider a time series of random variables S1 to Sn. Okay? So S1 comes, then S2 comes, so it's a time series, right? Well, the joint probability of these random variables is this, right? What is this? This is chain rule in probability, also called multiplication rule in probability, right? So probability of S1, it makes sense. Probability of S1, then given S1, what is the probability of S2? Then given S1 and S2, what is the probability of S3? And so on. Okay. Now, there was a scientist, mathematician named Markov, who said something interesting. He said, when S1 comes, okay, then I have probability of S2 given S1, okay, so far. Then I said probability of S3 given S1 and S2, right? But the information of S1 is kind of encapsulated in S2. Why do I need to condition on both S1 and S2? Let me only condition on S2 for S3. Then I go to S4. In general, I should say probability of S4 given S1, S2, and S3. Markov said the information of S1 and S2 is kind of encapsulated in S3. So let me only condition on S3, right? Right? So as a result, Markov said, let's only, for Si, only condition on S minus I rather than the whole before, right? This is called first order Markov property. We can also have second order Markov property, saying that for every Si, only consider on its two previous time steps. So for Si, only consider condition on Si minus 1 and Si minus 2, and not the before that, right? So second order, third order Markov property. But the intuition is interesting. When we have a time series, right? Because why do I mean by encapsulating information? So whenever I say probability of S2 given S1, kind of I'm encapsulating the information of S1 and S2. So for this one, I only can condition on S2. Of course, it's approximated. It's not exact. It's not exact. It's approximated. But this approximation is well enough. It's good enough. Okay? Did you get it? So as a result, this is relaxed to equation 3 by Markov property or Markovian property. Right? So whenever you hear Markov in machine learning, in mathematics, it should remind you of time series and probability. Okay, because his focus in mathematics was time series and probability. So it can be any order, as I said. Usually the default Markov property is order 1. So whenever we say Markov property, we mean first order Markov property, usually. A stochastic process which has the Markov property is called Markovian process or Markov process. A time series which has the Markovian property is called Markov process. Okay, that's one thing. And by the way, what is Markov model? Markov model in machine learning, in a statistic. So you have S1, S2, this time series. You can see it as a graphical model, right? You can model it as this, where every Si depends on its previous Si minus 1. Agreed? This is called Markov model. As you see, it's modeling a time series. Okay. Now, consider this. O1, O2, O3. In other words, every Si not only goes to S2, it also emits some observation. O standing for observation. Okay? So I have a bunch of states, a bunch of observations as well. Now let me put my eye here. I'm looking, do you see my head? I'm looking up from here. Okay? Then I only see observations. I don't see the states behind them, right? So the states become hidden, right? Or latent. Therefore, this is called hidden Markov model, or HMM. Okay, hidden Markov model. And why is it useful? It's useful for modeling time series probabilistically. Before, in ancient times, before the era of deep learning, whenever we were processing time series, people used to work with hidden Markov models. For example, for a speech recognition. Speech recognition is a series of phonemes, right? What is phoneme? A small, tiny part of the speech. These are phonemes, right? You can see speech as a time series of phonemes. Go back to the year 2000, or a bit before that, 1990s. You can see all of the papers on speech recognition are hidden Markov models. Or my thesis in masters, okay? My thesis in masters in Sharif University. What did I work on? Action recognition using Kinect sensor data. So we had joints of body, like Kinect sensor, right? And we were doing action recognition. Action is a time series of a bunch of body poses or states, right? For example, standing up, this is one state, this is another state, this is another state. Or this action, this is one state, one state, one state, right? Or jogging, this. How many steps is it? Kind of one step, second step. Repetition of these, okay? So again, you can see action recognition as a time series. We modeled it by hidden Markov model and Fisher discriminant analysis. We named it Fisher poses. But why is hidden Markov model very powerful? Can you tell me? Interestingly, it is robust to repetition. What do I mean? So the probability, if you can calculate the probability of one, this state, then this state, then this state. So I have 3 states, okay? Calculate this, the probability of this, the total probability of this time series. Now, calculate this, one state, second state again here, third state again here, then fourth state again here, fifth here, sixth here, okay? So the time series became longer with some repetitions. The probability will be the same. Now, when the repetition, the probability becomes the same, in other words, it is robust to speed. Consider the frames. This is doing it very fast. 1, 2, 3. This is slow. 1, 2, 3, 4, 5, 6, right? So it's robust to speed of time series. Very powerful, right? Now, Markov decision process, MDP. What is it? It is what is decision process? You want to make decisions, exactly like in reinforcement learning. You want to make decisions, right? So it's a decision process, which is also a Markov process. So you have the Markovian property, right? In other words, every state is conditioned on only the previous state. Every state is only conditioned on this previous state, first order Markov property, where all past information is assumed to be embedded in or encapsulated in the previous state. An MDP or Markov decision process is defined by a tuple, this. So S is a set of states. A small s means one state, and capital S means set of states. Okay. A capital is the set of actions, right? R is a set of rewards. And I have a reward model. What do I mean? The probability, the conditional probability of RT given ST and AT. By the way, what is RT? Whenever I have subscript T means time T, because it's time series, right? So RT is the reward at time T, ST the state at time T, and AT is the action at time T. And what is this probability? It says that this is my state. I do this action. What will be my reward? But this reward is probabilistic. So it's a conditional probability, right? So I have a reward model, okay? Also have a transition model in Markov decision process. So probability of ST given ST minus 1 and AT minus 1. What does it mean? In time T minus 1, this is my state. I do this action. What is the probability of the next state? happening, right? By the way, you can see it as probability of ST plus 1 given ST and AT, doesn't matter, right? You can see that. Discount factor, what does it mean? Assume I'm playing chess, a chess game. I sacrifice my queen. You might say, what a horrible player I am. But I might know that if I do that, in 10 moves, I will win. Did I do a good job or bad job? I did a good job, right? So the long-term reward is important, not immediate reward. But there is a but. Of course, I get happy if the reward happens sooner. So I'll have a discounted reward. What do I mean? I consider my reward at now, then my reward in the next time step, then my reward in the next 2 time steps, but discounted. Okay. Gamma is less than 1. It's between 0 and 1. As a result, can you tell me that gamma to the power of 0, here I have gamma to the power of 0, is larger than gamma to the power of 1, to power 1, then gamma to the power of 2 becomes smaller, right? So the larger the power of gamma, the smaller gamma to the power becomes. In other words, the more discount I have. Okay? Why do I have discount? As I said, sooner reward is better for me. Let me tell you with this example. Assume I sacrifice my queen. Of course, my total reward, my total discounted reward is good because I will win. But in one scenario, I might win in 30 moves. In one scenario, I might win in 10 moves. Which one is better? 10 moves. So that's why we discount. The sooner you win, the better, right? The better. So sooner rewards should be discounted less. Yes. So I have, by the way, if gamma is 1, then I have undiscounted rewards. So all of the rewards in the time steps ahead will be important. If gamma is 0, then I will only consider my immediate reward. Now, at every time step t, time slot or time step t, 0, 1, 2, 0 means now. 1 here, for example, means the next time step. The agent is at a state st, okay? Then it takes an action at, okay? By this action, it moves to a new state. Whatever you do, it changes the situation of the environment, st plus 1. If it doesn't do anything on the environment, st plus 1 will be equal to st, okay? So far. So, and st plus 1 is probabilistic. This means sampling, right? Sampled from this conditional distribution. St plus 1 given st and at. This is the transition model. Do you remember? Transition model. It receives some reward, RT, according to the reward model, right? Again, it's probabilistic. What is policy? Pi. So I'm defining important things in this slide deck. Important. These are important concepts in reinforcement learning. So what is that? One of the important concepts is policy. So one of them was reward that I already talked about. The other one is policy. What is that? It's a mapping. What is map in mathematics? You know, function is a special case of map, right? So a function is a map where you can't map the one thing to 2 things, right? To several things. So map is more general than function. Is a map from state to action. So from the state space to action space. Also, it maps state to action. What is the difference of these 2 notations in mathematics? This means map. This means the relation of spaces before and after map. So this is a space. For example, have you seen this R2 to R3? Right. This is also a space. By the way, you can see a space as a set, right? This is also a set. So the set beforehand goes to set after this map. So this is for relational sets before and after. But this is for map. Okay, so you should note the difference between these two in mathematics. Where were we? Okay. So I'm saying that the policy is a map from state to action. So it says that for this state, what should I do? What action should I choose? Agreed? So far clear? So for this specific state that I'm seeing, what action should I choose? What is the good action to do? This is policy. As you see, the output of policy is action. Okay, let me tell you one thing. In reinforcement learning, for you to understand very well, you have to understand the essences. What do I mean by essences? For example, in physics, when you have an equation, the essence of the left-hand side, if it is kilogram over seconds, the right-hand side should be kilogram over seconds, right? The essences of the two sides of the equation should match. Agreed? In physics, this is very important. Whatever, because some people call it dimensions of the size of equation. I call it essence. Essence of the sides should be equal to each other, right? So essences are important. Let me tell you, action and policy have the same essence. The essence of policy is action, because the output of policy is action. We have at least two important essences in reinforcement learning. Essence of action, essence of reward. We will see one by one different things in reinforcement learning which have either the essence of reward or the essence of action. So far, we saw action and policy. They have the same essence. Okay. We also have reward, which has its own essence. Keep it in your mind. Okay. Now, this policy can be either deterministic or stochastic. What do I mean? It can be either probabilistic or no deterministic without any probability. If it is deterministic, this becomes a deterministic function. Given ST, what is my action, AT? Or it can be sampled from this conditional distribution. So this becomes a probability of AT given ST, right? You can see this, by the way, as sample. What is the goal of Markov decision process? By the way, let me tell you that the goal of, we haven't yet started reinforcement learning. We will, okay? I'm talking about Markov decision process. The goal of Markov decision process, as well as the goal of reinforcement learning, is finding the best policy. You want to know what to do, what is the best to do at every state of the environment, okay? To get the most reward. So far clear? So the goal is this. So what is this? Can you tell me? This summation. This is the total discounted rewards. So expectation of rewards with respect to the policy. With this policy, what is my, expected value, right? Expected. Gamma to the power t is the discount, right? Summation from t equals 0 to h. What is h? The horizon, right? So from now on until some horizon, I calculate my rewards. This horizon, again, it depends on the user. It can be until the end of the game or until some window, okay? So this is total discounted reward. When t equals 0, it's at now, t equals 1, one step ahead in the future, etc. Maximize with respect to pi, the policy, but argmax. What does it mean? So which policy maximizes this reward? It gives me pi star, the best policy. Can you tell me what if I remove arg from here, only take max? What is the essence of that? So what is the essence of this summation? The essence of this summation is reward. I told you, let me repeat again. We have two essences in reinforcement learning, reward or action. What is the essence of this? Is it action? No, it's reward. So maximize this summation is also in the essence of reward, right? But I have argmax, where argument is policy. So the essence of argmax here is action. Did you get it? Is it clear? Clear? Okay. Bellman's equation or Bellman equation. the most important equation in reinforcement learning is Bellman equation. You see it over and over again in different topics of RL. Bellman was a scientist, so it's named after him. Okay. So what is value? Now I'm introducing the next important thing in reinforcement learning, and that's value. Value, you can see it the same as reward, but the maximum reward. See, at every stage, whatever I do, I get some reward. One of these things one of these actions is the best action, which gives the maximum reward. Let the maximum reward be named value. Okay, so the best or maximum reward is called value. So what is the essence of value? Reward. Reward. Okay. It's the maximum or best reward that the agent can get in some state. Okay, now consider the horizon. Okay. Now I want to come backwards from the horizon, from the end of the horizon until now. Why is it easier to do backwards analysis? Because when you do backward analysis, at the end, you know what happened. For example, you play chess, and at the end, you know you won, you lost, or it was a draw. All right? Yes? So at the end of horizon, you know what happened. So backward analysis is easier. Okay. By the way, there is a famous quote by Soren Kierkegaard, a famous philosopher, who said, life can be understood only backwards, but you have to do it forwards. It's interesting sentence by him. Okay, so consider a time period or horizon H. Now the last time slot, you tell me, what is the value? I just told you. The maximum reward, right? Maximum reward. The reward is a function of a state and action. Do you agree? In this state, I do some action, I get the reward. Okay? So maximize this with respect to the action. Which action I do in this last step, so I win. So I get the reward, maximize that. I call it the value at state ST. So far clear? Now, let me come one step back in the horizon. Okay? So VST minus 1. What happens? This part is the same as before. Again, you in the state ST minus 1, what action AT minus 1 I should do to get the maximum reward? And this is not argmax, this is max. So it's in the essence of reward as expected, because the essence of value is also reward. So far, clear. But there is an additional term. What is this? This is, forget this probability for now. This is gamma VST. What is VST? The value of the next times. Because you need to also consider the discounted value in the next time step, which was the last time step. You already calculated that here. Why didn't I have this in here? Because this one was the last time step. There was no step ahead of that. You don't have any discounted value after it. But one step before that, you need to consider the discounted value in the next time step, right? And I discounted by gamma to the power 1 because it's one time step ahead. Now, what is this probability? This is a conditional probability. This is a transition model. From this ST minus 1, if I do this action AT minus 1, what is the probability that I go to the ST? Right? Right. Now again, you can come to the 2 to last time stop. Likewise as before. Right? Now consider I want to write a general formula for this. This is called Bellman equation. It's this. So basically it says that every time step t, my value equals my maximum reward at that time step. However, I also consider the discounted reward in the next time step. Okay, the next time step. Also note that Do you see? It's a recursive equation. Here I have VST, here I have VST plus 1. Do you see the recursion? Okay, that's one thing. Also, I have this probability transition model. Why do I have this summation? Summation over ST plus 1. Guys, please tell me. If you tell me, it means that you have understood. Why do I have this summation? Assume I'm in the game. I'm playing a chess. Assume. This is a chessboard with some realization, some state. I can do a lot of things, right? I can move the pawn, the rook, the queen. Whatever I do, the next state will be different. So I should sum over all possible next steps, right? Agreed? If you ignore this value here in the summation of probability becomes, this probability becomes 1. Probability of going from ST to ST plus 1, but I sum over ST, all of the ST plus 1s. This becomes 1, but I have this value here, right? So I'm basically considering all of the possible next states, and I discount that. Okay? You might be wondering, why don't I have gamma to the power t? No, this happens. The gamma to the power t happens if you replace this recursion with its formula. So VST has VST plus 1 in it. VST plus 1 has VST plus 2 in it. If you put, so VST plus 1 has some gamma in it. Gamma times gamma becomes gamma to the power 2. Right? You will have that. Okay. So this was Bellman equation. Let me tell you one thing. In terms of notation, RL papers are a mess. Okay. Every RL author writes its own notation. You can see, if you compare two RL papers, you might see two different notations. There are a bunch of standard notations that they are using, but they are not using the same notation. I don't know why they don't standardize it. So sometimes they use a subscript T for time, T. Sometimes they completely drop T in their papers and they put nothing or prime. Okay. When they put nothing, such as S, they mean at this time T. When they put prime, such as S prime, they mean at the next time slot. So rather than ST and ST plus 1, they put S and S prime respectively. Okay. They do it for simplicity. As a result, you can see Bellman equation in this way too. So rather than ST, I put S. Rather than AT, I put A. Here also A. Rather than ST plus 1, I put S prime. Okay. So far clear? Also, they write Bellman equation in different ways. There is another variant of that they use expectation for Bellman equation. So they say, rather than maximize the reward, they say what is the expected reward with respect to S and the action. Okay. By the way, there's another difference. Here, sometimes rather than action, you can put policy. Policy S is action, right? Do you remember? Action was policy S. Again, I will go back to what I said to you. Always consider the essences. The essence of action and policy is the same, so you can replace them. Okay? Here, rather than A, you can also put pi S. So far clear? So basically, this is expectation of R given S and A. You might see this in papers. You might see this in papers. You might see this in papers. Okay? And here, rather than action, also have put policy S, where policy is equals A. So far clear? Okay. So we covered Bellman equation, which was one of the most important equations in reinforcement learning and Markov decision process. Now let's solve MDP. What was the goal of MDP? We said you remember? We said let's find the best policy which maximizes the reward, the value, right? So let's do that. There are two ways to do that. How do we maximize the reward? Two ways to do that. Either value iteration or policy iteration. Okay. Let me tell you. So again, I emphasize that we haven't yet started reinforcement learning. We are in Markov decision process. So value iteration and policy iteration, at least in these things that we are talking about right now, they are not in RL. They are in Markov decision process. I will tell you what is the difference between Markov decision process and reinforcement learning. Okay. So consider this. So we say, let's consider this backwards, again in the horizon. So recall Bellman equation and how we derived that, right? This is exactly what it is doing. That derivation analysis that we had, they are using that as an algorithm. So at the end, V star 0 means the end of the horizon. We get the maximum reward, and then we come back in the horizon and we calculate the value, right? And as you see, we will have a bunch of values, V0 to VH in the horizon. And after that, after we find the values, that's why it's called value iteration, because we are iterating over the values, over the Bellman equation, right? And the Bellman equation was value. So far clear? Then, because I have a bunch of values, I will have a bunch of policies. And I think you agree that in the horizon, in the time slots, different time slots, I will have different policies, because the policy depends on the state, and the state depends on the time slot, right? So here, for policy 0, again, I say, which action maximizes the reward? Argmax. Argmax is in the essence of action, right? It's not max, it's argmax. What about t greater than 0? This is also argmax, I apologize. Argmax. But I also considered the discounted rewards in the future. And consider that, note that this is the whole thing is in parentheses. So argmax the whole thing. Okay. For all actions, I do that. For all states, sorry. What do I mean for all states, by the way, in the algorithms? Here, I'm using state S, but which state S? Every state S. So basically, the whole thing can be either inside a for loop, or you, as an input, you'll say, for this state, do the value iteration. Okay. And the policy here is non-stationary. It means that it is time dependent, obviously, because it depends on state and the state depends on the time. It becomes more interesting. Just bear with me, okay? It becomes more interesting. Policy iteration is another algorithm for that. In policy iteration, we have two steps. Policy evaluation. I apologize for these typos. Policy evaluation and policy improvement. What do I mean? In the real world, you want to improve something. What do you do? In the real world, you have something you want to improve. What do you do? You evaluate it, you check how good it is, you improve it. By improving that, it changes. So you evaluate it again, you improve it. You evaluate it again, you improve it until it converges. This is exactly what we're doing. So we have some policy, okay? We first evaluate how good this policy is, then we improve it. Then we check how good it became, well, we improve it. We do it iteratively, right? Now you tell me, I have some policy. How do I know whether this policy is good or not? What should I do? I should calculate the reward or value. The reward and value are the same, but value is the best reward, right? So basically, I calculate the value with that policy. The larger the value, the better that policy. Then I improve that policy. When the policy changes, the value changes. So I evaluate the value. Then I improve the policy. Then I evaluate it by value. So this is, as you see, policy evaluation. This is policy improvement, right? Interestingly, in both of them, I'm using Bellman equation. As you see, I'm telling you, most of our algorithms in RL are using Bellman equation. Okay, but you might say how? The first one is the Bellman equation itself. In the second one, I have arg of Bellman equation. Bellman equation itself is in the essence of value or reward. Arg of it, with respect to action, arg max of it becomes policy in the essence of action. Right? Interesting. So, yes. Okay. Now let's compare value iteration and policy iteration. Here, give me a second. Okay. Do you see this? Compare these. So compare this line in value iteration and this line in policy iteration. They're all more or less the same. Bellman equation for value, right? In other words, value iteration has iteration over values until convergence, and then once it calculates the policy or calculates the policy. Okay, but in policy iteration, we do it iteratively. We calculate value, we calculate policy. Again, we calculate value, we calculate policy. So one of them iterates over the value as much as it can. Then once it calculates the policy, that's its value iteration. Policy iteration does it alternatively. Value, policy, value, policy, value, policy. Right? Okay, that's one thing. We can also compare them in terms of time complexity. So without proof, accept it from me that, yes. Convergence, it means that it doesn't change. So what do I mean? Until some point, so initially, the value of previous iteration is very different from the value of next iteration. Gradually, the difference becomes smaller and smaller because the policy is getting better and better, and we'll have one best value. So the change of, as long as the change of value is large and the change of policy is large, it hasn't converged. If the change of both of them becomes small, it means that it has converged in policy iteration. In value iteration, whenever the change of value is small, then it's all. Oh, by the way, in value iteration, sorry, we have 4 in the horizon, 4 loop in the horizon. We don't have convergence. Okay. In terms of complexity, that's also important. Value iteration is complexity is S squared A. What is A? By the way, the cardinality of S, what do I mean? Number of states that I have. Cardinality of a state. Okay. Cardinality of A means number of actions that I have. So the time complexity of value iteration is big O notation of number of states to the power 2 times the number of actions. But for policy iteration, the time complexity is state cubed plus state squared times action. Which one is worse? Policy iteration, of course, right? Policy iteration is worse. But you might say, then why do we use policy iteration? There is one thing. This is a number of iterations. But what about each iteration? So the number of iterations in policy iteration is larger, right? But yes, but No, I apologize. I apologize. So this is the time complexity per iteration. I apologize. Okay. So which one is worse? Policy iteration. What does it mean? I will do more things in every iteration of policy iteration. Okay. But you might say, so policy iteration was worse, but I'm saying no. In practice, we have seen that policy iteration has fewer number of iterations, and value iteration has more number of iterations. In other words, let me say it in simple words. Value iteration has a lot of iterations, each of which is small. Policy iteration has fewer number of iterations, but each iteration is big. So they both have pros and cons. Did you get it? Did you get it? Now, of course, every time when we have two things with pros and cons, someone will say that and says, let's have a middle case scenario. Okay, let's have an interpolation between these two algorithms, and that's modified policy iteration. What does it do? It says, let's have an interpolation between these two algorithms to have the best of two worlds. Okay, so as you see, it's a hybrid of value iteration and policy iteration. This for loop inside is like value iteration, but these two together is like policy iteration. So basically, it says that do the policy iteration, but in the policy iteration for the policy evaluation, do it k times for k times rather than one time. And doing that for k times imitates what we did in value iteration. Did you get it? Is it clear? Okay. So it's called modified policy iteration. And in practice, we have seen that it works better and faster. It converges faster. By the way, yeah, I already said that. Here, the action is in the policy evaluation is replaced with the policy S, right? Because I'm evaluating the policy in the Bellman equation, right? Okay. Now, Markov decision process is explained. Now we start reinforcement learning. We just started, okay? What is reinforcement learning? It is similar to Markov decision process. Well, you need a break? Okay, so let's have a break. Maybe it's a good time to have a break and come back at 2 to 9. Is it good? 2 to 9. Okay, so reinforcement learning is similar to Markov decision process that we talked about, but a transition model is not known in it. What do I mean? Do you remember in Markov decision process, we had transition model. What was transition model? Probability of ST given ST minus 1 and AT minus 1, right? So given state and action, what is the probability that I go to some other state? I don't have it in reinforcement learning. The rest is the same as Markov decision process. As a result, reinforcement learning is more realistic than Markov decision process. Why? Because usually in real world applications, we don't have that transition model. We usually don't have the probability of going from this state to another state given with a specific action, right? We don't have this probability. Otherwise, we would know what would happen if we do this action, right? In real world applications, we usually don't know that. So that's RL is more realistic as a result. But the goal of RL is the same as goal of MDP, finding the best policy for giving the best, for having the best reward or value, right? So as you see, it's like MDP, only the line for the transition model doesn't exist. Okay, we have two types of RL in the literature, model-based RL and model-free RL. Model-based RL finds a transition model, so it becomes like Markov decision process and then solves that, okay? But model-free RL says that I don't care about a transition model. I assume my transition model is implicit, and I solve it. Okay. Usually in the literature, when we say RL, by default we mean model-free RL. There are fewer researchers, in my opinion, who are working on model-based RL. For model-based RL, I don't have much knowledge about it, but apparently, for example, if you have a robot, they move the robot arm from one state to another state, and then they calculate what probability is for going from this state to this state, these things, and then they model it, and then it becomes a Markov decision process, and they solve it, right? But in model-free, you don't do it. You go for it without knowing the transition model. Here we are talking about model-free RL algorithms. Okay. By the way, references 4 and 5 are surveys on each of these categories. Temporal difference evaluation, another important thing in reinforcement learning. First, let me tell you about Monte Carlo evaluation. In the model-free RL, the value, we need to estimate that. We need to estimate the value. What was the value? The reward, the best reward. So we need to estimate. Given a policy. So with this policy, what is my reward? Note that I don't have a transition model. Okay. Without any transition model. Recall the expected total rewards. This is expected total discounted rewards, right? With respect to the policy. And this is also, if you remember this, we can call it as a value, right? That was also the first term in the Bellman equation, that you can see it as a value, right? But how do I calculate this expectation? In practice, in mathematics, expectation is expectation. But in practice, how do you calculate expectation? Either you can use the definition of expectation, okay? But it's hard, because in definition of expectation, you need the probabilities, right? Another way to do that is called Monte Carlo approximation. What is Monte Carlo approximation? Again, if you see this tutorial paper, where was that? Give me a second to find it. Monte Carlo approximation. It's this. Okay, this is for continuous form, but here we say it for discrete form. Let me tell you what it means. You know mean, right? What is mean? M-E-A-N, right? Mean. What is that? Another name for expectation. Okay. Mean is expectation. What is average? Summation of them over the number of them. Is average mean? No. But public people, they usually use this interchangeably. Why? Because mean of some distributions is average. Okay. Public people, as well as programming languages such as Python, when they say mean, they mean average, right? np.mean takes average, right? Or you go to the streets and ask, what is the mean of these values? They will say it's the average of them, right? But they are different. Why do public people say that? Because the most common mean is average. Why? Because the mean of several distributions, including Gaussian distribution, is average. Okay. Mean of not every distribution is average. Mean of some distributions, such as Gaussian, is average, right? But so Gaussian distribution is the most common continuous distribution in the world. Why? Why? Do you know central limit theorem? Okay, I'll tell you briefly, but Google it later and read its Wikipedia. Central limit theory. It says that when we have a bunch of values, they might be from different distributions, but they're independent. You add them up. When you add them up, the distribution of the addition becomes Gaussian. Shocking. Shocking. The more values, then the more number of values, number of points, the more accurate this is. The more accurate it becomes like Gaussian distribution. So when n, the number of points, you limit it to infinity, this becomes actual Gaussian distribution. And in physics, we have a lot of additions of signals. The light that I see is an addition of a lot of light rays coming to my eye. In physics, everything is added to some other thing, right? So in the real world, we see a lot of additions. According to the central limit theorem, the real world is full of Gaussian distribution, right? That's why even in our eyes, the cells of our eyes act like Gaussian distribution or Gabor filter. I already talked about Gabor filter to you, didn't I? Gabor filter. So Gabor filter has also Gaussian distribution in it on some exponential operator. So that's why we can approximate expectation or mean with average. Okay. So this approximation is called Monte Carlo approximation. Okay. So assume I have a bunch of data points. Do you agree that these data points have some distribution? And this distribution has some mean. When we say expectation of this, we mean that we are referring to the mean of this distribution, but we don't have that, right? It says you can approximate the mean of this distribution of these points by the average of the points. The larger the sample size, the more samples you have, the more accurate this approximation is. So far clear? Okay. So as a result, this quantity, so by the way, expectation of x, I can approximate it by 1 over n summation of xi. Right? So expectation of f of x, a function of x, you can also approximate it by Monte Carlo approximation as average of f of x. Okay? This is called Monte Carlo approximation. So here, also have a function of rewards, f of x. So I take this is average, right? Average of them. I replace expectation by average. NS, what is that? The number of times that I see the state, S. How many times? So I'm playing, I'm doing stuff in this environment. How many times I see this specific state in my playing? Does this happen a lot? Right? So NS is the number of times that I see the state S happens. RTK is the reward at time T in the horizon and the kth episode. What do I mean by episode? Here, I'm playing the game from start to the end once, then I play it again, and again. When I said approximated by Monte Carlo approximation, so you are approximated by the average of the number of times that this state happens, but across what? I need to play again and again, and see how many times this state happens, right? Assume I'm playing chess. I play it once from the start to the end. Either I win or lose or draw. I restart the game. I do it again. Play again. I play 100 times, for example, right? Each time I play is called an episode. They also call it a trajectory. So different names in the literature of RL, okay? Because you can see that a trajectory of the actions, right? So trajectory or episode. So in the kth episode, my reward at time t, I denote it by RTK. Okay. So that's one thing. NS is the number of times that state S is happening, and as the average, the Monte Carlo approximation is over the number of times that the state is happening. The larger the NS, the more I see the state S, the more accurate this approximation. Okay. So the agent should play in the environment for k times. An episode, as I said, is once we play the game completely. By the way, again, it depends on how you define it. Either you define the episodes until the end of the game. Some people, they consider it as a window. Doesn't matter. Okay. Consider this game. This game is called random walk in reinforcement learning. Okay. So you start from this state D. You go. So these you go to these different states, and at these states the reward is 0, 0, 0. But in the very right state, the reward is 1. In the very left state, the reward is -1. I start from here, state D. And the actions are going right or left. Okay. The policy is a stochastic here. So what do I mean? Randomly, I go this with according to some probability, right? The probability of pi. Then maybe this, maybe this, maybe this. Randomly, I go until I maybe end up here. These are terminal nodes. Whenever I end them, if I end at G, state G, I win with reward 1. If I end up in state A, I will lose with reward -1. Okay, so this is the game. And for a particular policy, the game is played for k episodes. Okay, every episode is represented as a trajectory ending on either node A or node G, right? And the Monte Carlo evaluation is the average of total rewards across the trajectories episodes that we have. By the way, in a few slides, I will solve this game. At least one iteration of this game, you will see how cool it is. Okay. There is a problem with Monte Carlo approximation, also called Monte Carlo evaluation. What is that? It needs a lot of iterations. You need to play again and again and again for the Monte Carlo approximation to be accurate, because you need to do it. NS should be large, right? Right? So that's problematic. What should we do? We work out something named temporal difference to replace Monte Carlo approximation. Recall that we are doing all of these to estimate the value given a policy. We don't have the transition model. Okay. Now I define the total discounted rewards by I denote it by GK. Okay. GK is the total discounted rewards for the kth episode. So far clear. What was the Monte Carlo approximation of value? It was this, right? You remember? I'm using this equation 12, but rather than this, I'm using G. Okay. Now what happens? I'm saying that, do you agree that summation of GK from 1 to n, I can write it as GNS, the last GN, plus the summations where k goes from 1 to ns minus 1. Agreed? Then I have this. So do you agree that according to this equation 14, can I write it as VNS minus 1 S is 1 over NS minus 1 summation GK, k from 1 to NS minus 1. Do you agree? I'm simply putting NS minus 1 rather than NS here. So now, as a result, this, which is this, equals this times this, which is here. Okay? Now, so GNS over NS is here. I have minus VNS minus 1 over NS, which is here. I'll also have NS times VNS minus 1 over NS. So I will have VNS minus 1. So simply I multiplied this to these elements, okay? What happened? Interesting. VNS pi s became VNS minus 1 plus some other thing. Did you see? So basically it says that the previous value in the previous ns minus 1 plus something becomes the next value. So this is, here I write it here. I'm rewriting it here, VNS. This, by the way, again, I said there is a mess in the notations of papers. Sometimes rather than NS, they simplify it by N. They say N, okay? When they say N, they mean NS here, okay? So Vn pi S equals Vn minus 1 pi S plus this, they usually denoted by alpha N. Alpha N is 1 over NS, okay? This Gn and this, right? What is this doing? It is an incremental update. Every previous Vn minus 1 plus something is the next one, right? And then you can do it, you can calculate all of the Vn's incrementally. Agree? Start from n equals 1. V1 equals V0 plus something. Then V2 equals V1 plus something, right? Agree? So this is what we had found. Now, temporal difference basically says let's replace Gn with this. And it makes sense. Why? So what was Gn? Gn was the total discounted reward. Again, consider the essences. Total discounted reward, essence of reward. They're replaced with something else, which is in the essence of reward again. Reward plus gamma discounted previous value. Again, in the essence of reward. So it makes sense in terms of essence. So they replace Gn with this. In other words, what are they doing? Recall Bellman equation. This was Bellman equation for value. Okay. Basically, they say here, rather than so this is the total discounted value. Gn is the whole thing, right? This is, do you agree that the Bellman equation is also the total discounted reward, but recursively, right? So here they say rather than expectation, I only approximated by one sample. Approximation of expectation with one sample means Monte Carlo approximation with one sample. It is an awful approximation, but it's still they do it, okay, and it works. And what is this here? When you have one sample, you only have one next state. So the summation goes away, and you will definitely go to the next state. So this will be 1, and you will have V pi S prime with gamma behind it. So basically, they are replacing this with this Bellman equation, but approximated with one sample. Okay. This is called temporal difference evaluation. So basically, as you see, what are we doing in this equation? We are finding value, right? We are finding value. In Monte Carlo approximation, we were also finding value. Agreed? You're also finding, which one is easier? Temporal difference. In Monte Carlo approximation, you need to play again and again. In temporal difference, you go one step ahead and see what happens in the value, right? So that's why they don't do it by Monte Carlo approximation. They do it by temporal difference, as in equation 70. Okay. By the way, if you find this topic hard, because RL is hard, okay, and it's hard for everyone. Don't think that it's hard only for you. Okay. You need to study it, and you will absorb it. Okay. Anyway, do you remember I said rather than 1 over ns, we put alpha n, right? So they say we can have any function of n, such as 1 over n, but with some conditions. With some condition. That the summation of alpha n from 1 to k, right? Where k goes to infinity. What do I mean? Alpha 1 plus alpha 2 plus alpha infinity should become infinite. Okay? But the summation of their squared shouldn't become infinite, should be less than infinite. An example is 1 over n. For example, what do I mean? Let me think. 1 over 1 plus 1 over 2 plus 1 over 3, etc. It becomes infinite, I guess. You need to calculate this summation. Recall calculus 1. But 1 over 1 plus 1 over 4 plus 1 over 9, etc. It doesn't become infinite. Okay? So 1 over n satisfies these two equations. These are sufficient conditions. What do I mean? If these two conditions are satisfied, alpha n is good for us to use. And by this, we will find the correct value. The correct value. By the way, note that this temporal difference is iterative, right? You can see it similar to iterative optimization, such as gradient descent, right? Iterative, that's why this alpha is also called learning rate, right? The previous V plus something else is the next V. It's iterative, similar to gradient descent. That's why alpha is also called learning rate, right? So by default, they usually use 1 over n, where n is the number of times that the state S is visited. So instead of trying to calculate the total future reward, temporal difference simply tries to predict the combination of immediate reward and its own reward prediction at the next moment in time. Only next moment in time. This is temporal difference. Now let me tell you what it means in some real world example, what it means to use temporal difference. Consider we are doing weather prediction. Okay. For example, assume that the actual temperature of Monday was 20, today is 20, and I predict tomorrow to be, so Monday is 20, I predict Tuesday to be 19, and Wednesday maybe to be 18, something like that. Okay. Now, so tomorrow comes. Now I'm in tomorrow, and I see that I'm in Tuesday, and I see that, oh, the temperature became 23. So I made a mistake. Okay, so I made, how much did I make a mistake? 23 minus 19. Let me scale this mistake by alpha. This is my temporal difference. Okay, now I can correct my predictions for Tuesday and other days of the week by this amount. See? So I can wait and see what happens tomorrow and compare it with my prediction and see how off I am. If I'm too much off, this temporal difference becomes big. I need to add all of the next ones with this temporal difference, or the next one tomorrow, Wednesday, with this, right? Again, I wait, and Wednesday comes and I see how much difference I have. Then I update my prediction for Thursday, right? Did you get it? This is temporal difference. The algorithm is simple. Basically, we are having a loop over that update of temperature. This is the update, right? Where S prime is an S in the next time step. So I have my input is the policy pi. Okay. So for this policy, given this policy, I want to estimate my value, right? How good this value policy is. By the way, when I say I want to estimate the value, why do I want to do that? Can you tell me? Because I want to evaluate my policy. Okay, I have some policy. How good is it? Let me evaluate my policy. How do I do that? I can calculate the value, the best reward that I can get by this policy. So while value is not converged, execute the policy. It gives you the action, right? So you have the state S. By this action, you will have the next state S prime. Then you increment ns, the number of times that you saw state S. Then you set alpha, the learning rate, to be 1 over ns. You use this temporal difference to update your vs with the policy pi, right? And then you go to the next state and you do it again. until convergence. And then you return this value. Basically, this algorithm says how good the policy is. Without any transition model, this is a miracle. Without a transition model, I could, by just interacting with the environment, I could see how good the policy is. The next important topic in RL is Q function. Okay. So do you remember we said value? We also said reward. Value and reward had the same essence, right? Q function is the third thing which has, again, the essence of reward. So three things, at least in RL, have the same essence of reward. Reward itself, value, and Q. What about action? Action itself and policy, they have the same. So reward, value, Q have the same essence. Action, policy have the same essence. Okay. What is Q? So we had a state value, the value at the state S with the policy pi, right? We can also define some value which is a function of a state and action together. Do you remember what was value? The best reward that I can get, so I maximize my reward with respect to action for value. Recall Bellman equation. But Q, it doesn't say the best reward. It says that in this state, for this action, what is my reward? Did you get it? Did you get it? Why do you seem bored? Are you bored? Aren't you excited about the beauty of this algorithm? This is very beautiful. So this is called state action value rather than a state value. It's also called Q function. Okay. Now, so as I said, a state value is V, shows how good to be in a particular state S. But Q function says how good it is to perform action A by policy pi in the state S. Okay. Now, whatever we had for reward and for value, V, we can have it for Q. So, for example, recall Bellman equation for V, which we have Bellman equation for Q. Rather than V, I put Q. Here, rather than value, I put maximum Q. Why? Why don't I have maximum here? Because value itself has maximum in it. Value is the maximum reward, but Q doesn't have maximum in it. So I need to maximize the Q with respect to action, next action. Agree? Do you remember that we can also write Bellman equation in let me remember. Oh, now this is Bellman equation, but this is putting best value in the optimal value in the Bellman equation, V star. We can also put optimal Q in the Bellman equation, Q star. Okay. When I say star, it means optimal. Now, do you remember? So assume I have Q star SA, the best optimal Q function for the state S and action A, right? Maximize it with respect to A, so the A goes away, it becomes like value. It becomes a function of state only. The value which is a function of the state only is V, right? Not Q. It becomes V star. What? And it makes sense because they both have the same essence, reward. What about argmax of this with respect to A, action? So this is in the essence of action. As a result, it's pi star, which is also the policy, is the essence of action. We can also find pi star by argmax of total discounted reward with respect to the policy pi. The expectation is with respect to the policy, right? Okay, do you remember temporal difference for value? We can also have temporal difference for Q function. So this is temporal difference that we talked about for value. Now replace V with Q, QSA. Okay. Interesting. And GN here is as before, is the total discounted reward. When I say one trajectory Monte Carlo evaluation, do you know why? Because do you remember in Monte Carlo approximation, I had average of some stuff. That was that stuff. So average of that thing over NS multiple runs, right? This is only one run in the Monte Carlo evaluation. Anyways, we can have policy. Do you remember we had policy iteration for value? Do you remember? For value V. Now we can have policy iteration for Q function. You see that? So again, initialize the Q function with a random value for every state S and action A. Let it be random initially and you update it to become optimal. How do you do that? What is this? Policy evaluation. What is this? Policy improvement. Do you remember? I said, evaluate the policy, improve the policy. Evaluate the policy, improve the policy. In previously, we evaluated the policy by value V. Now let's evaluate the policy by Q function. Using the temporal difference equation for Q function. Do you see that? And so I use temporal difference for policy, temporal difference of Q function for policy evaluation. Then I say argmax of Q with respect to A, but argmax. So it's in the essence of action. So it gives me the pulse. Right? Now Q learning. Now Q. You might be angry at me right now because I'm teaching a lot of things, but you will be thankful to me, I think, the next semester or next years, because I'm teaching almost one course of RL in one session. And okay, I think it will be useful for you. Q learning. But so, where were we? Do you remember this value which we evaluated? This is Bellman equation, but evaluated in by Monte Carlo evaluation using only one trajectory. Do you remember? And I said it's an awful approximation, but they do that. Do you remember? They use it in temporal difference, right? Likewise, this approximation for Q function is this. So as I said, whatever we have for value V, we also have it for Q function. So here I have action rather than policy, right? And as you see, this is action rather than policy. Rather than V, I have maximum Q with respect to A prime. What is this? The Q function for the next state and the next action. But maximize with respect to next action. What do I mean? In the next state, what is the best reward that I can get across different actions that is possible to me or possible to me? So in the next state, whatever I can do the best thing, which is the best reward, best Q, right? So far clear? Okay. Again, I replace the expectation with one R within one sample. I'm approximating within one sample. And for one sample, I only have one S prime. So this becomes one, this summation goes away, only have one of them. And I will have gamma maximum this, right? Now, do you remember in the temporal difference of value, we replaced G with this. Now in temporal difference of Q, we replace G with equation 26. As a result, this was G in incremental updates, right? So I'm do you remember or don't you remember what I'm talking about? Here, I'm talking about this slide. Where was that? Where was that? Here, this was incremental update. I replaced GN with this to get the temporal difference. I'm doing this for Q function now. I get equation 27, right? Now, what is this? Updating Q, right? So random Q, you have random Q, you updated Q, and it becomes better and better gradually by temporal difference, right? What are you using for this update? Can you tell me? You are using S, A, S prime, A prime. What are these? Current state, current action, next state, next action. But also reward, current reward. Okay. Using these, I'm updating my Q function. And my Q function says how good it is to be in this state and do this action without any transition model. This is a miracle by reinforcement learning. Just by purely interacting with the environment and finding out what is good to do. Okay. So compare it to the updates in do you remember value iteration? This was value iteration. Value iteration was used, do you remember, in Markov decision process. Q learning is used in reinforcement learning. Okay. And Markov decision process, we had the transition model. In Q learning, we don't have the transition model. Okay. Now, I think it makes sense why we use Q learning in reinforcement learning. Why? In Markov decision process, I have the transition model. So it's just suffice to me to calculate the value at every stage. But in reinforcement learning, I don't know where I should go. The probability of next state given the previous state and the previous action. So I need to use a function which is a value, which is a function of both state and action. Do you see that? We didn't need that value to be a function of both state and action in Markov decision process because we had a transition model. But in reinforcement learning, we need to calculate the values for different permutations of states and actions. So this is Q learning. What is that? Basically, it uses a temporal difference of in the Q function, and that does it iteratively, right? So until Q star is not converged, select and execute some action. I will tell you how to do it. Okay. Select and execute some action. You might say how. We have different algorithms to find this action. Okay. Do select some action. Then you will, by this action, you will have the next state S prime and some reward, right? Then you increment NSA. Recall that this time alpha n for Q function is not 1 over NS. It's 1 over NS and A. What do I mean? NS and A is the number of times that the state S and action A are observed together because we are using Q function. This state, action A, observed together. But for value, it was only the number of times that the state S is observed. Okay. So I'm using these or any function which satisfies those two sufficient conditions, right? For alpha n. And then I use the temporal difference. And then I go to my next state until convergence of Q. Then I return my Q. You know how simple this is? Do you know? Forget Q. Forget the whole thing. Benjamin is previous Ben plus some alpha something, some delta. This is exactly what they are doing. Don't see it as a monster or something. For until previous Ben is similar, next Ben is similar to the previous Ben. This is exactly Q learn. Now replace Ben with Q. Okay. So initially, if Ben is awful, because I assume my Ben is initialized randomly, right? If my Ben is awful, my delta is large in initial iterations. In each iteration, delta is changing, right? Delta becomes smaller and smaller by Ben getting better and better, until the alpha delta becomes very, very small, very small. It means that convergence of Ben. Now replace Ben with Q, right? So initially have some random Q and S and A. What do I mean? Randomly say that if I, in this state, if I do this action, this is my value. Who said that this value is correct? You update that value using this temporal difference. Do you get it? Now we'll see some action, some example. Oh, by the way, before that, how do we find this action A? We can either find selected randomly, random, right? Random action. In this case, you will have exploration. What do I mean? I explore different things in this environment. Right? Or I can find the best action based on my Q, right? Based on my Q, I know, based on my current Q, I know what is the best action to do. The max, arg max Q, S and A with respect to A. This is the best action, right? Right? If I do the best action, I have exploitation. I only do the best actions that I see in this environment. It means that I might get stuck in the local best, right? So there is a trade-off between exploration and exploitation. Exploration, I explore the whole different possibilities, but it takes time to converge. Exploitation converges fast, but it might not be the best solution, right? As a result, I can have a middle case scenario, right? I think it's called epsilon greedy. So with some probability, I think epsilon, they explore. With 1 minus for epsilon probability, they exploit, or vice versa, as man. Okay, that's one thing. Another thing that we can do is that we say that initially, in the initial iterations, let me explore, because I don't know the solution. Let me choose random actions. But gradually, in the later iterations, let me exploit only. Find the best, because I'm supposed to get close to the actual solution, so let me not oscillate a lot around it. Okay? This is a good example of Q learning. And by this, I think you will get a lot excited. So consider this random walk game that we had. Now, you tell me. So assume that the current Q function at this iteration, in the iterations of Q learning, in this iteration, assume that I'm in a state D, okay? At this iteration for states and in this specific iteration, these are my Q values. Q, you know that Q is a function of both state and action, right? So state D, going right, action right. Let it be 16 in this iteration. State D, action left, going left. Let it be 10. It makes sense. Why? Because in this game, if you go right, you will win. If you go left, you will lose. So this Q, at least in this situation, makes sense. Q of right, going right, in D, state D, is larger than Q of going left. If it was the other way around, it was an awful Q, so delta would be large, right? It would change the Q in a way that Q of right gets larger than Q of left, okay? Then Q of, in state E, Q of right, going right is 20, Q of going left is 15. Again, it makes sense, okay? Now, assume at the current iteration, we are at the state D, and we choose moving to right. This moving to right can be chosen either by epsilon greedy, randomly, or by best action, whatever, okay? I chose moving to right, okay? Now, what is my S, state S? It is D, right? I'm here at the state D. My action is right, going right. What is my next state by this action? State E. I go to E, from D to E by going right, right? What is my reward in this current state D? Is 0, right? Now, assume the number of times that I saw D and right is 2. Okay? Assume. So far. And let the discount factor be 0.9. Why usually discount factor is close to 1? Why? Because I want to have a lot of discounts in the horizon. Okay? I shouldn't set it to 1 because I want to have discounts. It shouldn't be close to 0 because close discount is very small. Close to 0 discount factor means that I don't have any discount. I only consider my immediate reward. So I usually set it to be close to 1. Maybe 0.9 is good. Okay? Then in this situation, by performing this action at this state, what happens to Q, D, and right? Do you remember? In the Q learning, I'm doing this step. QS. So let's update that. Q of D and right becomes previous Q of D and right. What was previous Q of D and right? 16. Right? What is alpha n? I just told you. Let n be 2, so it will be 1/2. What is R? Reward was 0 for this state D. What is gamma? 0.9. What is this? Next state is E, right? Recall that here I have S prime, and I know that my S prime is E. But I'm maximizing Q of E and A prime with respect to A prime. So basically, how many actions are possible in state E? Left or right, right? So I should maximize between this and this. I have 2 actions possible in E. If I had 3 actions, I need to maximize over 3 things, right? So maximum of 20 and 15, of course, becomes 20, right? So as you see in temporal difference, I'm also considering in the next state, what is the best thing to do? What is the value of best thing to do? Minus QD and right, which was 16, which is also here. If you calculate these, becomes 17. So basically 16 got updated to 17. Does it make sense? Yes, because we went right. And going right will yield winning the game because of this last one. And now you can do it iteratively. And the Qs will change in a way that in this game, all of the Q any state and right becomes very large. All of the Q any state and left becomes very low. Maybe close to 0. But Q any state to the right becomes very large, maybe 20, 30, right? So that after this learning this Q, after training in the test phase, now we just do argmax of Q and S and A to do what action to do. Of course, whenever you start from D, it says go right. You are in E, it says go right. In F, it says go right, win. That's it. Okay?
The first state, the D.
Yes, in this game.
And to the left, where value come from? Is randomly?
So yes, so as do you remember I said select and execute action A? In the training, this is for training, right? In the training, you can either do exploration or exploitation, or you can start with exploration by selecting random actions, and then gradually you do only find the best action. You know what I mean, right? Exploration, random action. Exploitation, I mean argmax, Q, S, and A with respect to A. Okay, so or you can do epsilon greedy with some probability. You do random action with some probability. You do best action, and you can also change this epsilon, the probability, depending on whether you're in the initial state, initial iterations or the last iterations of training. In the initial, you need to do more exploration and less exploitation. And then, so in the training, you do this, you do this update, you do this update, right? Iterative update. Then you converge, you will have some queue for states and actions. In the test phase, you only do argmax QSA in every state. Very interesting. And the miracle is that we didn't have the transition model. Purely by interacting with the environment, we could find some queue functions. Let me tell you one brief sentence. In the next session, we'll continue this, but the idea is this. Now we have the queue function, we want to approximate it. So let's approximate it by some function. This function can be linear or nonlinear. One of the important nonlinear functions that we can approximate things with is neural network, because it has nonlinear activation functions in the middle of it, right? As a result, we can use neural network to approximate queue function. And this is what they did in DeepMind before joining Google, right? And then we'll introduce deep queue networks or DQN, and we see how it was used for solving the Go of game. The game of Go. Game of Go. Yes, yes, that's it. Any question? No? Okay, thank you very much. By the way, the next week, Monday, we have a session, the last session. On Friday, we have presentation. And please, by the way, why don't you evaluate me in the system of Guelph and also rate of my professor? I requested that in the announcement. Please evaluate me. I appreciate it. In both your Guelph feedback and in my rate my professor. Thank you very much. I appreciate it.
For the presentation, so as a team, we submit one PowerPoint file enough, or everybody has to send?
No. Only one representative.
Then
doesn't matter.
Member just use that file to do the presentation.
No. Everyone in the team should present. For submitting only. For submitting.
You need only one the same PowerPoint.
Yes. But for presentation, you need to divide your presentation between all people in the team.
Who is presenting this part, right?
Yes, you decide.